This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 2 weeks. Thanks to our audience and the partners listed on our website for supporting the podcast.
This is Robert Blumen. I'm here at QCon San Francisco 2009 with Philip Zeyliger. We'll be talking about the Hadoop project today. Philip, welcome to Software Engineering Radio.
Hi, thanks for having me.
So please tell the listeners something about your background.
Sure. So my name is Philip, and I'm an engineer at Cloudera, which is a startup that was founded about just a little over a year ago. And we're focused on all things big data and Hadoop. Before Cloudera, I worked at Google, and I worked at a hedge fund called D. Shaw.
Thank you. So to start off, what is Hadoop?
So Hadoop's a system for two things. It has two main components. It has a distributed file system that stores data. It has Hadoop Mapreduce, which is a system for processing and analyzing that data.
What is the problem domain that Hadoop is the solution for?
So Hadoop's problem domain is when you're dealing with more data than you can fit on a single machine. So usually it's certainly more data than you can fit in a single machine's RAM, but also more data than you'd want to read, from the disk of a local machine. It just takes too long. So what you do is you split up the problem into lots of smaller problems, have many computers dealing with that, and then you stitch it all back together.
So what are some of the real-world forces that have driven the emergence of this problem domain?
So this problem domain certainly in its current incarnation comes from the web. Google developed Mapreduce and GFS, which are the technologies that Hadoop is based on, to index their massive crawls of the web. It's what they used to sort of make their search engine happen. Since then, it's come into use in a couple other applications, but it's all still pretty heavily web, and a lot of it is still pretty heavily web-driven. There's, if you have many servers, they all produce many logs. And so, for example, a lot of companies analyze every single click that happens on their web page. They record it, and then later they analyze it to train stuff. And now we're seeing it emerge into more traditional enterprise applications, stuff like finance and bioinformatics. And those are newer uses.
What are the design goals of the Hadoop project?
The ultimate goal is to be able to do processing on a large scale, sort of both storage and processing, that you're not able to do. And how does that come out? It comes out of being able to do work that's not possible to do on one computer, just because a given computer can only have 32, 64 gigabytes of RAM and can only store 1, 2, 12 terabytes of disk. So being able to spread that out so that you can do things that weren't possible before. Another goal is to let users utilize clusters of computers as if they're just the cluster. The users shouldn't need to know super specific details. They should just say, hey, run this job. Let me know when the result is in. And the system should take care of splitting up that work, farming it out to a bunch of anonymous machines, and bringing it back. You shouldn't need to know, the host names from machines 1 through 17. You should just say, hey, my cluster is called cluster. So those are, that's sort of the framework in which we think about Hadoop.
Is it more typically driven by large volumes of information like logs, or the core transactional data of the enterprise that records its sale of its good or service?
It's certainly driven by a lot of the existing stuff is driven by logs. Either stuff that your machines produce, stuff that corresponds to page views or ads displayed or clicks. It also makes sense, in the financial world. Every time we swipe your credit card, that's a transaction. It's very similar in some sense to a click, right? Some user somewhere did something, and I think it'll be useful for a lot of that sort of transaction as well.
So could you give us some of the more prominent use cases that you're aware of, or examples you're aware of people in industry using Hadoop?
So certainly Hadoop is used to build indices left and right. So this is the bread and butter stuff. There's Hadoop used to analyze, logs, sort of figure out what's going on a website. Facebook based their entire data warehouse on Hadoop, and they've built, they've contributed a lot of code and built up a lot of it. And they're interested in questions like who's using our Facebook? Are they using this new feature that we just released? What, did this experiment work? What things should we show people? A lot of batch processing of that sort, as well as batch processing that. So there's both ad hoc analysis and there's batch processing to make the business run. So stuff like optimizing ads, computing page rank type of stuff that could, that's batch processing that's part of your production workflow. And then there's ad hoc analysis of sort of more researchy stuff.
So how's Hadoop different than a relational database?
So the biggest, they're different beasts. It's true that both of them can store data and both of them let you query that data in some way. But they've got pretty different characteristics. Most databases are in the domain of one computer. There's several very good cluster databases. They're usually in the domains of single digits computers. Hadoop tends to scale a little bit bigger for you can do it on hundreds and thousands of computers. So that's one difference. Another difference is structured versus unstructured data. Databases only let you have structured data and more or less structured processes. Hadoop lets you do either. It's less, you don't have to fit into the mold quite as much. There's some disadvantages of that, and there's certainly lots of stuff on Hadoop that's been developed to deal with specifically structured data. But if you're doing, web page analyses, web pages are inherently sort of unstructured. There's all this messy text. It doesn't quite as much make sense to do that on a database platform. They're usually complementary technologies. There's certain parts of your business that make sense to store in the database, certain parts of your business that make sense to operate on with Hadoop.
So how is Hadoop different than a networked file system?
The biggest difference is some of the computation happens on the same machines that are storing some of the data. So whereas in a network file system, you inside of that big black box that you've bought, the big storage area network box that you've bought, there's probably a couple computers and there's probably a bunch of disk drives. And you can, they're very good at sort of offering you data, letting you read and write, handling multiple writers, all that sort of stuff that file systems are good at. Unfortunately, there's a bottleneck of, what's the network pipe, even if you have 24 disks in there that each can read at 50 megabytes a second or even 100 megabytes per second. What's the pipe that you can get there to that network file system so that you can actually process your data? So Hadoop is, lets you distribute the computing all over the nodes that are also storing your data. And there's some technical trade-offs. They have different, the Hadoop file system is not good for your everyday NFS workloads. In fact, it's not just not good, it doesn't work. It doesn't let you do all of the operations that POSIX prefers you to be able to do. But it's very good at storing really, really large data sets in disparate files and then also processing them.
So can you give us a high-level view of the architecture of Hadoop? If you had to break it into the pieces at the top level, what are the pieces?
Sure. So first of all, there's two halves. There's the Hadoop distributed file system and Hadoop Mapreduce. Just talking about HDFS first. So HDFS is based on GFS, which is the Google file system, and there's a paper, and it's a pretty simple model. There's a central machine. In Hadoop terms, this is called the name node, which stores all the metadata. When you go to write, create a file. When you go to rename a file. When you go to read a file, you always talk to the name node, get some metadata about that file. This is typically pretty small. This is all held in memory in the name node. Then there is every computer is running a specific server, a specific daemon, called the data node daemon. And the data nodes are actually responsible for storing the individual blocks of files. So what happens is, say you're writing a gigabyte file. First of all, what you do is you split that up into 16 64 megabyte blocks. Each of those blocks is then written to 3 data nodes. Not all the blocks have to be written to the same 3 data nodes. Blocks are, as you write them, distributed to 3 data nodes. And there's some smarts about which data nodes it picks. It tries to sort of diversify the racks. It tries to balance it out. So a given file is stored in triplicate, but it's stored in triplicate across, with these block boundaries. So that's the architecture of GFS. What's really nice is it's very fault tolerant, because if a machine dies, GFS picks up on it a little bit lazily because people...
You mean HDFS?
Yeah. HDFS and DFS are a little bit synonymous when you're sort of close in the code. So it's a good reliability story. When a machine falls over, either because its disk failed or it fell off the network or it spontaneously burst into flames, whatever happens, HDFS notices that block now only has 2 copies, and it goes and asks one of the copies to copy that, to make a copy onto some other machine. So it, centrally coordinates making sure that there's always 3 copies of a given file. So that's the HDFS side of the story. The Mapreduce side of the story is there's a central daemon called the job tracker. The job tracker is sort of the scheduler for the cluster. It shares some of the characteristics that traditional sort of high-performance computing schedulers handle. You give it a job, and it goes and it makes sure that job executes. Now, to execute that job, it farms out the work to task trackers. So usually a typical cluster, sort of to imagine a typical cluster, you have a couple machines that are special. They're well cared for. You make sure that they're happy. And then all the other machines are worker machines, and they're running both a data node, and that's sort of lets them use their local disk, and a task tracker, which lets them which lets the system schedule computation on that machine. One of the cool bits is that the job tracker is able to find out about where the data is, and so it's able to schedule computation locally to the data. So say you have a file, and since it's a big file, say it's a copy of, say it's all of your log files for your website for the last year. There's a bunch of files. They're all really big. Your website's really important. It's a great website. So the blocks of this file are scattered all over the system. And all you're doing is you're doing some simple record-based computation on these. So what you do is you ask Mapreduce to do this computation, and it's able to schedule the computation so that the computation usually happens on blocks that are local to the machine that's doing the computation. And if not, machine local, rack local. And that makes, sort of in terms of hardware provisioning, it makes your networking system more happy. There's more network bandwidth left for other stuff. So that's the interplay between Mapreduce and HDFS. HDFS is by far the most common input and output sort of source for Mapreduce. Mapreduce uses HDFS to read the input and dump its output at the end.
What assumptions about the network architecture does HDFS make?
HDFS makes the assumption that everything is local, in the sense that HDFS is not a system that you run on a wide area network across your 2 data centers. You're usually running it within a single data center, and you're running it in a data center whose network is good. It's well taken care of. There's some redundancy, because ultimately every data node, might have 2 to 12 disks. In aggregate, that bandwidth might be from anywhere from 100 megabytes to a gigabyte a second. And it might be called upon to take that bandwidth and stream it to another machine to do some processing or to do copies or whatever. So typically the network should be pretty good. It's certainly oversubscribed because the economics works out that you typically oversubscribe it. But the network topology is usually pretty strong. You typically divide your system into racks and do it's a traditional tiered thing. It's not the only way to do it, but it's a common one.
What sort of scheduling philosophy is the job tracker using?
There's actually a couple different schedulers, and they're pluggable a little bit in the code. Almost all of the schedulers are doing a couple things. So one, they're balancing total throughput of the system versus latency. And the thing that's happening there is sometimes there are tiny little jobs that only need to do a little bit of data. And it would really suck for them to be queued up behind the job that takes a week to run, because their user would be way happier if they ran, within the next 10 minutes and not next week. So there's that thing that they're worried about. Another thing they're worried about is scheduling individual job tasks of the job. So jobs are broken up into tasks, and each task may have a machine that its data would be local on. So scheduler is worried about making sure, optimizing that to make sure that there are data local tasks going on. Another thing that schedulers worry about is, say you have an organization and there are two groups, and each of them wants a 30-node Hadoop cluster. You as a CIO, CTO type of person should say, hey, why don't you guys buy one cluster of 60 machines and share it? Because then you'll both have more capacity when the other's not using it. We only have to do one, level of administration, and it'll be great. But people are like, well, what if they're running jobs and our jobs don't get to run? Doesn't that suck for us? So there's a thing called the fair scheduler, which tries to make sure that even though when the cluster is idle, you can use up all of it. If there's competition for resources, it can allocate them according to some configuration that roughly says, do no worse than if there were two 30-node clusters. So there's some work in that regard. And there's actually some really cool research work coming out of Berkeley that deals with the scheduler.
When Hadoop's running a job, where is the resource limitation? Is it typically CPU, network throughput, or disk? Or does that depend?
It depends very much on the job. We've seen all of it, certainly. A lot of traditional sort of data warehousing workloads are just disk-bound because they're sort of reading all the data, doing some very simple aggregations. CPU time is fairly negligible. One of the funny things is you could do a trade-off there, because if you compress your data more, you can sort of save bytes, but it'll take some more effort to uncompress. And if there's some things that you're doing that are very CPU intensive. One thing you might be using Mapreduce to do is to do some Monte Carlo simulations of something, and you're just using it to spread out this work across 1,000 machines. Well, then your Monte Carlo simulation is CPU bound. There's phases in Mapreduce, sort of the shuffle phase, which is between the map and the reduce phase, where a lot of data has to go between there's n squared-ish network connections that are going on, and the data has to transfer all over the place. That phase may often be network bound, depending on your topology, depending how much data is generated, depending how many reducers there are, all that sort of thing.
Can you describe the failure modes that Hadoop is designed to handle properly?
So Hadoop is designed to withstand the loss of individual sort of data node task tracker machines. So, before we talked about how there's typically you have a whole host, maybe 100 machines that are both data nodes and task trackers. Any one of them going down does not cause data loss. Doesn't cause data loss. And also, whatever tasks are running on that machine, the job scheduler picks up that they failed for whatever reason, be it hardware failure or cosmic rays, whatever happened, picks it up, assigns that work to a different machine. The user never even knows unless they look, their job parts of their job got executed multiple times in part. So that failure is really well handled. And that's the main type of failure. If you have stuff like network partitions, if one rack falls down, Hadoop has some smarts in it that data is usually replicated off rack, and it should be able to recover from that. But if you've got a full-blown network partition, there's only so much it can do, and it expects you to eventually reconnect the network back so that it can bring the bits together.
We've been talking for a few minutes about HDFS and the scheduling aspects. Now let's pop back up to the top level and go down the other branch, which is Mapreduce. Tell us, what is Mapreduce?
So Mapreduce is a framework for doing computation. And it's a really clever model. What happened was the folks at Google, this is Jeff Dean and Sanjay Gamawat, who wrote the paper and drove a lot of Google's infrastructure, realized that they kept doing the same sorts of things again, and they kept running into the same problems about how to deal with failure, how to do the network transfer. And so what they came up with was a pattern of where they divide the computation into 3 phases, 2 of which the user has to implement some code for. So what happens is in the map phase, the framework, and the framework takes care of a lot of things for you. In the map phase, the framework gives this user-defined function, this map function, some data, and the map function emits some other data. And then the framework kicks in and does this big sort by a key of the data that the mapper emitted. And then the reducers come in, and they get all the data grouped already and sorted by this key. And there they again invoke a function that you defined, and then you get to do some more processing. And then the Mapreduce framework, helps you write that out to the output file. One other thing that's going on there is the Mapreduce framework is taking care of all the failure conditions of how to split up files. There's a lot of sort of stuff under the cover that Mapreduce framework takes care of for you, so that you as an as a developer can focus on your core business logic analysis, whatever you're trying to do, and the framework takes care of a lot of the stuff.
Could you walk us through failure handling of, let's say, an instance of map fails?
Sure. So let's say you have your job running. There's a mapper, and the machine spontaneously combusts. So the first thing. Let's say it doesn't spontaneously combust. Say your process dies for whatever reason. First thing that the job tracker typically does, so the task tracker on that node says, hey, this process died. Dude, what's up? And the job tracker notices that this process has died, either because the task tracker told it or because the process hasn't checked in a while. There's some heart beating going on. And so it says, this process died. Well, okay, try starting it again. And typically, if the machine didn't fail, but just the process failed, it'll start again on the same machine. It'll try running. Maybe it'll fail again. And then the job tracker says, maybe it's just that this machine sucks. Maybe there are bad neighbors. Maybe there's some other failure of this machine. Maybe this machine is configured incorrectly. So then it kicks it off to a different machine entirely. Eventually, if there's enough failures, at some point it triggers the overall job to fail. And there's sometimes you sort of say, don't trigger your overall job failure if 90% of the tasks complete, because it's okay. If a machine spontaneously combusts, usually what happens is the job tracker notices that the task hasn't been reporting any progress and goes and starts it off somewhere else. A key part of this is that there's an explicit contract that between you, the programmer who just wrote these map and reduce functions in the framework. And that contract is, hey, the framework can run your map function on the same data as many times as you want. So if you're doing something evil, like talking to systems outside of Hadoop, you better damn well make sure that it's idempotent, that you can run it multiple times, and that's okay. If you only expect it to, if that's not okay with you, you don't get to do that, right? If that's not okay with you, you have to try something else. If you're sort of following the contract and you're just emitting keys to give to the, keys and values to give to the reducer, that's less of a problem. It knows that those keys and values that you emitted aren't valid because they came from a job that, a task that failed. And so, it essentially tells people to ignore that.
You're starting to describe the programming model. You start from the top and say, what is the programming model? What parts does the framework provide, and what parts does the programmer provide? How much work do they have to do?
So essentially the programmer has to, so the traditional MapReduce programming model, the programmer has to provide 2 functions. A map function, which takes keys and values and emits any number of keys and values. And a reduce function, which takes a key and an iterator of values and produces any number of keys and values. That's the basic model. You can implement a bunch of things with just that. There's some complications. There's things called combiners and partitioners and input formats and output formats. We're just not going to talk on them yet. That's the basic model. One thing that's happened in the Hadoop community that's really great and cool is that people have been building higher level languages that take other forms of expressing the problem instead of just straight out implementing the map and the reduce function, and translate it into the map and reduce functions under the covers. They run MapReduce jobs. They write essentially MapReduce jobs for you. And those frameworks are Pig and Hive, and maybe we'll cover them later in this interview.
So let's come back to that because I want to talk about Pig and Hive, but I have another question about the programming model. So programmer use whatever is their favorite programming language to implement map and reduce.
Yes. So the native, for Hadoop itself, the native API is in Java. And so Java has the most, is in many ways the most functional. It's the highest, it's the most performant. It's one of the most commonly used. There's some hooks to sort of call out to sub-processes, which can be written in any language, Ruby, Python, Perl, choose your poison, that let you write Hadoop map and reduce functions in those languages. So there's this thing called Hadoop Streaming, which takes care of this sort of wrapper that call out to the sub-processes and defines an API that your scripting program needs to use. And so that your Hadoop itself communicates via streaming through standard out and standard air to your program. It's really easy to whip up one of these streaming programs, even if you don't know Java, even if you don't want to deal with all the complete making the jar files and all that stuff. That's not as quick, and it's used actually very widely for a variety of reasons. Either because people like their scripting languages better, because the performance doesn't necessarily matter. It's not the only factor. Development time is a huge factor, or it's more convenient, more expressive, what have you.
Okay. Does Hadoop help you out with pushing the jars or the scripts out to all the nodes where the computations occur?
Absolutely. So there's something, as part of job submission, it pushes out things to all the nodes to run them. It actually uses HDFS to do that. And there's also something called the distributed cache, which helps you push out auxiliary files, and they get placed into the current working directory of the individual tasks. So if you have some auxiliary files, some data files, what have you, you can just push them out using that, and that's really handy.
You hinted at this. Is Hadoop entirely implemented in Java?
Hadoop is almost entirely implemented in Java. Actually, there's a couple bits where it can optionally call out to a JNI native library. For example, it has some hooks to use native zlib. And that's just, all that stuff is there for performance reasons when it's there. It runs perfectly fine without any of it. But typically, if you're running on Linux, you'll also compile the native libraries and use that.
Is Hadoop supported on any operating system that has a JVM?
Hadoop is mostly used on the Unixes. So it's very heavily used on Linux. I think there's a good amount of FreeBSD usage. There's some Solaris usage. A bunch of the Hadoop developers use OS X sometimes. So it works on all of those systems. It tends to work as a client on Windows, but almost nobody is running it, or nobody that I know of is running it, the servers on Windows. So nobody would object to it working, but it's open source, and so as far as I know, it doesn't work out of the box in Windows.
Is there art of tuning the Hadoop cluster to run your job efficiently?
There's definitely an art to making sure that there's some parameters. There's plenty of knobs. More knobs than there ideally there would be, I'd say. And so there's definitely an art to it. You get better at it over time, and there's some things like counters that Hadoop has that tell you a lot about your job. And then you can do some quick back-of-the-envelope calculations and figure out sort of what's going on.
Could you give me either a war story or just a classroom tutorial if somebody called you and said, my Hadoop job is running too slow? What are the first few things you're going to look at?
Sure. So the first thing you look at is you look at the counters and see how many bytes it read. and you sort of take the number of bytes it read, divide it by 50 megabytes per second, and compare that to the job time. And if it's reading, let's say this job read 200 megabytes. This is a bad example. So let's say it read 200 gigabytes. You would expect that to take 400 seconds. If that's roughly what it's taking, okay, it's disk bound. That's what's going on. So if that's not what it's taking, you do some deeper analysis. You want to figure out whether sort of things are configured with the right amount of memory. Ideally, your cluster is configured with some sort of monitoring framework like Ganglia or something. So you look at the CPU usage, you look at the memory usage, you see if the machine's swapping, you see if the disks are full, take a look at your network graphs. So there's some holistic stuff. You can use some sort of, there's some support for profiling. There is, sometimes you sort of debug the job and figure out whether it's doing something stupid. Typically what you do is you look at the job a little bit globally, and then you try to reproduce it on small sets of data and sort of, if you do want to do optimizations, you just want to do them with small amounts of data and see what you can do.
Has anyone in the community or commercially contributed anything like a dashboard or a Hadoop analytics to help with the process of archaeology?
Yes and no. There's some products that are helping people both develop Hadoop applications and sort of monitor Hadoop clusters and that sort of thing. I work on one of them called Cloudera Desktop, which lets you interact with your Hadoop cluster from a web interface, and you get to look at some state about what the different machines are doing. You get to look on all these job details that are pretty easily available. There's not yet a magical magic crystal ball that tells you exactly what's wrong with your program. Probably there never will be. There's definitely space for better tools to tell you more information about your programs.
Let's come back to Pig and Hive. Let's start with Pig. What is Pig?
Pig. So Pig is one of the higher level languages developed to write Mapreduce programs without writing the map and the reduce functions. So it was developed at Yahoo, and it's used very heavily within the Yahoo organization and in other places to do a lot of their Mapreduce processing. It's a data flow language, so you sort of declare variables that are data sets, and there's grouping, and there's some join operators. It's a little bit, if you're a database person, it's a little bit more like specifying the logical plan than it is specifying the query. So it's less declarative and more data flow. It's in a short number of words and sort of a few lines, you could save yourself quite a few lines of Java, and that's partially because Java is boilerplatey and partially because Pig has some really expressive operators. So that's Pig in a nutshell.
What would be a typical use case for Pig?
You can do many of the things that, lots of counting and aggregation. Pig is a really good fit for, because it'll have the built-in operators to do some of the counting, and it'll have sort of group bys and that sort of thing.
Tell us about Hive.
So Hive is a different approach to a higher level languages than Pig. It was developed at Facebook for their sort of data warehouse. And what it does, it exposes sort of a SQL-like shell. So you write statements that look a lot like SQL, and it keeps track of a mapping between files and sort of schemas. So if you tell it about certain files that are in your file system and what those files look like, sort of in a columnar fashion. And then you write queries, and those queries themselves get run as Mapreduce jobs. Both Pig and Hive, in many ways, are doing the same things, and there's actually some efforts to make Pig, to make Pig also support SQL-like queries, to sort of add that part of the equation to it. Both of them have optimizers, and both of them are capable of running jobs that span multiple Mapreduce jobs. So you can't, if you want to do a map and a reduce and then another map and then another reduce, that requires two Hadoop Mapreduce jobs. And that's fine. That's not a problem at all. You just submit one after, the second one after the first one finishes. And both Hadoop and Pig, use that to sort of do more complicated things that can't be expressed in a single Mapreduce.
So it would be accurate to say Hive is a language that provides higher level abstractions on top of Hadoop that then compiles down or interprets down to a series of Mapreduce jobs.
That's accurate to say about both Hive and Pig. They're both higher level languages that both affect Mapreduce programs.
So the data warehouse engineer or the SQL programmer is going to be maybe more comfortable with the interface that looks like Hive or Pig than with writing map and reduce jobs in Java.
Right. I mean, it takes for certain tasks, it takes a lot of the repetitiveness out, even for the well-seasoned Java developer. And it also exposes Hadoop to an entire classes of users that aren't as, don't want to be in the weeds with Java programming. They just want to write a quick little thing. And so it's like any other high-level language. You lose some flexibility. You lose some insight into what's going on optimization-wise, but you get fewer lines for your expressiveness.
Can you tell us about what are some of the other more prominent sub-projects in the Hadoop ecosystem?
Sure. So there is the Hadoop Distributed File System, HDFS, and the Hadoop Mapreduce. Both of these build a lot on this project called Hadoop Common. Those used to be all one project, so that's one thing. Hive and Pig are both sub-projects. We just talked about them. They're the higher level languages. Zookeeper is a set of, is a system and a set of primitives for coordination amongst processes that let you do sort of master election and coordinate that sort of thing across processes. That's also a Hadoop sub-project, also largely developed by folks at Yahoo. There is HBase, which is a clone of another Google system called Bigtable, which is a distributed key value store. So you put keys in and you get values out, and it manages that for you. It has a whole bunch of servers, and it uses HDFS underneath.
How about Scoop?
Scoop is not technically a sub-project. It's a contributed module in Hadoop Mapreduce. So Scoop is this component, this program that was actually developed by a coworker of mine at Cloudera named Darren Kimball, which lets you extract data out of a database into HDFS. It can use JDBC or it can use some sort of more optimized things to do so. The point is, why would you do this? You've already got it in the database. Isn't the database more expressive? Often what you want to do is, you've got some stuff in the database already, and then you've got this huge stream of other stuff, and you need to reference one or the other, as you're processing. And so this lets you perhaps synchronize parts of the data that you have in your database that you really need, with, into this other framework where you're doing some other processing.
So I might use Scoop to import a bunch of user records, and then I could use Hive to join some of the data and the user records to data in my log files.
Yeah, exactly.
I spent a little time looking at Zookeeper. As far as I could tell, it's not built on top of HDFS. It's just an independent piece of functionality. Is that correct?
That's right. I mean, it's in the Hadoop umbrella because Hadoop is all about software that makes sense for cluster computing. And so it's one of the components that for certain applications, if you want to do coordination of a bunch of processes, Zookeeper is what you use. Typically what you'd use it for is small bits of data as opposed to sort of the massive amounts that Hadoop deals with. But with small bits of data, you can do more expensive consensus protocols.
What size clusters are people running Hadoop on?
That varies. The biggest are probably at Yahoo. Yahoo has, I believe, more than 25,000 machines, but that's split into actually many clusters. I think their largest clusters are in the 2,000 to 4,000 range. I think closer to 2,000, but my numbers could be a little off. Then there's plenty other users who are using hundreds. and then there's lots of people who are using tens and lots of people who are using one. So one is the development use case where you're running it on your laptop, you're exploring. It's not a practical case because almost certainly you could do it. You could lose the overhead and do things just faster with normal stuff. But if you want to have your thing scale nicely when you get 10 machines, when you convince your boss that this is the way to go.
Is there much interest in building Hadoop clusters on cloud infrastructure?
There is. Cloudera itself has some scripts that you can get on our website which let you start a Hadoop cluster on EC2 and then tear it back down. And it's really, really useful for experimentation, early phase stuff. As you use it more, you might stick with EC2 or you might sort of move in-house. Depends on where the other infrastructure is, and it depends on cost and all sorts of things. So there's lots of people using Hadoop on EC2, and there's and every other sort of cloud infrastructure provider, definitely.
If I had a 50-node cluster in my IT department, then I would run my Hadoop job on the 50-node cluster. But if I was going to run a job once in a while on a cloud, it's not clear to me how many nodes, and perhaps I want to minimize the amount of compute dollars I spend. Are there any rules of thumb for sizing your cluster when the size itself could be variable?
Sure. It depends on. So usually the cost thing, if Amazon charges by the hour. So if your thing runs for 10 hours on 2 machines, well, buy 20 and run it in an hour. You can divide by 10, so you take 20 machines and run it in 1 hour, and that'll cost you the same in Hadoop and EC2 because they charge by the hour. And as long as you're a little bit careful so that you don't get charged double.
Are you saying that then total compute hours will remain fairly constant for a particular job?
If your job is what's called embarrassingly parallel, yes. If there's other stuff going on, it depends on how much data you're reading, depends on, do you need that aggregate bandwidth of 20 machines versus 1 machine? So there's a lot of trade-offs. Ultimately, it's not that hard. I think you get a pretty good sense of it pretty quickly. So you figure out what your limiting gating factor is, and you multiply it out, and there's some pretty good back of the envelope calculations that you can do.
Let's talk a little bit about the Hadoop project. How's it organized? Who's the sponsor?
So Hadoop is an Apache Software Foundation project, which means it's open source. It's open source under the Apache license, which is a license very friendly to businesses. It's not infectious. It doesn't extend to the thing, so you can build on top of it and not release the things that you built on top of it to the world. And so that makes it friendlier to businesses. The core contributors to the Hadoop project are, in terms of companies, are certainly right now Yahoo and Facebook. There's a couple other companies, including Cloudera, that have one or multiple committers to the project. And it's run like any other Apache project. There's Hadoop PMC is project management committee. There's a set of committers. Committers vary depending on the sub-project also. And everyone, there are mailing lists. There's a Jira, which is a ticket system. So the basic flow is you file a bug on the Jira. You say, hey, this is not quite right. And then discussion ensues there. Somebody will post a patch. Maybe that's you if it's small and you knew exactly what you wanted, or you propose a change that's more complicated and lots of people chime in. Eventually there are patches. Eventually they get committed to the repository. Every once in a while releases are rolled. So it's, very typical Apache project.
Can you give us some highlights on the project roadmap for upcoming releases?
Sure. So it's an open source project, so it's reading tea leaves a little bit about what's going on. Hadoop 21, the release that's coming soon, it was feature frozen, I think a month ago, is going to have working append support, which is very exciting. It means you can write to your files, more than once. You can add to them, and this was really important for HBase. Long term for what's called Hadoop 1.0. This is at some point Apache Hadoop is going to produce a Hadoop 1.0 version. And the goals of that are some API stability. One of the things that's exciting that's coming to line is a new serialization framework called Avro, which we totally missed in our list of Apache subprojects earlier, which handles serialization and RPCs. And the plan is to substitute Avro for Hadoop's other RPC mechanisms. And so then you can talk to Hadoop from other languages, not just Java, just because you can speak the wire protocol more clearly and it's defined and documented and is a first-class API. Another thing that's in the pipeline is there's a lot of work going on security and improving that and Kerberos support and that sort of stuff. So that's coming down the pipeline too. Always there's performance improvements, always there's API improvements, always there's new knobs and features and fun things.
Are there any interesting books people want to learn more?
Absolutely. There's, I believe, 3 books, one by O'Reilly, one by Manning, one by A-Press. The O'Reilly one is written by one of my coworkers at Cloudera, Tom White, and is really good. The other 2 are probably really good too.
Would you foresee that someday Hadoop or something like Hadoop would be a standard part of operating system distributions, or do you think it will always be a separate entity that people will run on top?
Hadoop fundamentally runs on multiple computers. So, whether are there going to be standard operating system packages for Hadoop? Absolutely. Cloudera already provides RPMs and Debian packages. It's only a matter of time until those packages or something similar to them makes their way into Red Hat and Debian and whatnot. It's a slow process, but all software that gets used a lot makes its way into all open source software that's used a lot makes its way into that. It doesn't make sense really to say, is Hadoop going to be part of my laptop? Because Hadoop doesn't make sense if there's only one machine. So it's always going to be something that you install and configure sort of specific to your topology and your set of machines.
Tell us about Cloudera.
So Cloudera is a startup. We were founded a little bit over a year ago, and we're doing a bunch of things. We've got the Cloudera distribution for Hadoop, which is free and you can download, which is RPM and Debian packages for Hadoop. There's instructions on how to install it, that sort of stuff. So you can get them on our website. They're free. We have a bunch of training materials online that, there's videos and slides and exercises. There's a virtual machine that has everything configured and up and running that you can sort of work through those exercises with. We also offer training and certification as services that we sell. And we sell support and professional services to organizations. So organizations will come to us and we'll help them configure Hadoop, get started, or if they're already using Hadoop, we'll help them optimize and give advice and help them out with bugs in Hadoop, that sort of stuff. And we're also building some software around Hadoop and that ecosystem. One of the things I mentioned earlier, I work on Cloudera Desktop, which is more of a UI to talk to Hadoop, and that's one of the things we're building. And there's other stuff that's coming down the pipeline for all around Hadoop that's going to make sense, within that ecosystem.
Where would people go to get Hadoop?
So there's, the basic thing is go to the Apache Hadoop webpage. It's hadoop.apache.org, and that's the project's central page. You can, there's downloads and documents and all that stuff. There's also a couple distributions. So the Cloudera distribution for Hadoop, as I mentioned, has RPMs and Debian packages. The Yahoo distribution for Hadoop has a source release, which is sort of the bits that they run. Basically, the difference is people are always patching here or there a couple different things, and that's how it works.
People would like to contact you. How would they do that?
So you can email me. My name is Philip with one L at cloudera.com. That's cloud and era. There is I'm on Twitter at PhilZ42, so PhilZ42, and my company is on Twitter at Cloudera, and there's a blog and all the stuff.
Philip Zeyliger, thank you very much for telling us about Hadoop.
Thanks so much for talking to me.
Thanks for listening to Software Engineering Radio. Software Engineering Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig Reddit Delicious links and the /dot button. To contact the team, please send email to team@se-radio.net, or if it is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks to Charlie Crow and the Podsive Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.